Well, good morning. Thank you for all coming. It's a pleasure to see so many people here. It's a topic that is unusual, but I think will become increasingly necessary. And I'm particularly pleased as a CP guy because I'm going to talk about the practical methods of what happens below the water rather than what's happening above the water. And it's nevertheless very good to be able to speak directly to coatings engineers and the coatings companies, because it's very rarely that a CP guy gets to do that. We'll see what happens. Right. How do we mitigate the sustainability aspects of cathodic protection? Well, what is sustainability? The United Nations defines it as a generic concept, and you can see what they say about it. It's a bit woolly. How do I know what the needs of the future generations are going to be? As John said in his opening lecture. What we have is two tools, and they're the only two tools available to us to allow us to monitor what impact we have on sustainability. Firstly is an environmental product declaration, which Birgit has mentioned earlier. And the other tool is life cycle assessment. Let's look at the first one in relation to how it affects us as CP engineers. Well, it's simply a report, and it describes what a product is made from and how it impacts the environment across its entire life cycle. There are no guidelines in the marine industry for how you format one of these declarations. There are in the construction industry, and you need to be looking at ISO 14025 and ISO 14804, which detail the requirements for an EPD. They are incredibly complex and should be followed, but they are very lengthy documents. They need to address the environmental impact across the life cycle of the product. How do we know what the life cycle is? How do you know as coating suppliers what the life cycle of your product is? All depends on other factors. Depends on the structure design and what some other designer has determined how much of your product he needs. The life cycle impact, as I say, is dependent on factors that are outside our control. If you look at the next the next tool that we have, and this is a life cycle assessment. And this is a compilation and evaluation of the environmental and sustainability impacts of the product throughout its life cycle. This is very important because it has to look at the whole life cycle. And it is comprised of a life cycle inventory analysis, basically what the product is made of. For galvanic anodes, that might be the alloy, it might be the steel inserts, bit of cable, maybe some fasteners. For an impressed current system, it might be the anodes, the power unit, the cabling, the monitoring system, and so on. But then we have to look at the life cycle impact. And this is very difficult because we don't know what the life cycle is, as I've said before. We don't have basically much information to go on for any of our products, and that includes coatings as well. But it's going to be increasingly important. As Birgit has pointed out, new Danish regulations for the next wind farm are making this information mandatory from the suppliers. And in Europe, in the EU, there is already in force a directive compelling companies above a certain size to include sustainability reports within their corporate reporting. And the Dutch and German authorities already have existing regulations for supply chain management issues on sustainability. And it's going to be increasingly incumbent on all of us to produce this information. The information is going to be needed from project control for life cycle assessment and from manufacturers for an EPD. And I think an EPD will become part of the normal product documentation that we have to produce in much the same way that we produce a certificate of conformity or test certificates. It's all coming, and I think it's going to come more quickly than we expect. Right, so what we have to look at in CP terms is what the impacts are. Well, CP, for those of you who don't know, relies on the supply of a current, an electric current. You make the structure, the cathode of an electrolytic cell, the corresponding anode, which can be either galvanic, naturally producing the current, or impressed by an external power source. And the amount of current you need has direct sustainability impacts. And the amount of current that you need is basically the product of the surface area, the wetted surface area, and another factor called the current density, which is the amount of current in amps per unit area. And normally these are taken from various standards. On the offshore industry, the oil and gas industry, we've generally taken water depth to mean high water level, and that's been considered good enough. The new offshore wind farm standard, which Barry referred to, actually goes one step further, and it's more relevant with more inshore developments, and that is the water depth is not constant. It is related to the locality, whether it's near an estuary, it's related to tidal flows, and it's related on top of all that to wave heights. So this new standard takes into account and introduces a concept called frequently wetted depth, and the designer can choose how much surface area that he introduces into his calculations. On the current density side, again, current densities are being published in standards. They're determined by location and water temperatures generally. Many publications give standards. We don't think about them too much. We just take a book. It's safe. It's contractually safe. It says here, we can use it. We have to be cleverer than that. And there is then another factor, particularly for inshore waters, and that is water velocity. And if we look at the amount of turbulence that you get around a monopile, for example, there are many factors which affect the water velocity. Water velocity varies with depth as the water approaches the monopile. As the water goes round the monopile, it has to join up at the other side, otherwise you'll get a void. So it has to increase its speed around. And there are all sorts of turbulence factors as well. And the new ISO for offshore wind farm CP does take this into account and make some recommendations about the effects of water velocity on the current density. So we are making progress. We are making some effort to be cleverer in our CP designs. But the other big factor that affects the amount of current is the presence of coatings, of course. And the way that the CP engineer deals with the presence of coatings is firstly to recognize, and I'm sorry guys, that coatings are not perfect and they're not perfectly applied. So we take into account what we call a coating breakdown factor.
I think it timed out.
Okay, right. Yeah. And since for the last 40 years at least, we have used a linear model, looking at a factor based on a published rate in various standards for the annual rate in percentage terms of coating breakdown. And as you can see, it's a linear model. This is for an IM4 coating. The theory will tell you, if using the current coating breakdowns that are published, that coating might last for 80 years. I don't believe that. And DNV, who are the originators of this linear model, are quite open and quite explicit in their guidelines that the linear model is not accurate and it doesn't really address the issue, but it's a very easy calculation to make. So being quite lazy, CP engineers just do that. But what is the model for coating breakdown? Well, we know that seawater just absorbs into the paint film, and we know that when the seawater is absorbed into the paint film, it becomes less resistive. But we also know that the front, ahead of the absorption front, still remains resistive throughout the coating life. And we only get corrosion at the substrate when we have a conductive path from the open seawater directly to the substrate surface. So what might the real model, the actual model, be? Is it the top button? Well, the actual model might be, we don't start at 0%, by the way, because we recognise there is some coating damage before the coated structure hits the water. There will be a gradual increase over the years in the coating breakdown factor and therefore the amount of current, because you get blistering, you get inadequate cross-linking and all that kind of thing, and some mechanical damage to the coating. But once the conductive path starts hitting the substrate, then you'll get a dramatic increase. And this is important to the CP designer, because the difference between the two curves is a direct measure of the current we need, or the current that we actually have to provide for. So if that red curve, the actual curve, is something more close to reality, let's say a 30-year design life, the final current is something like 7 times what we actually need. And we have to provide for that current, even though if that current is not going to be used. In galvanic anode terms, it generally means for a coated structure, more anodes. For an impressed current system, we have to have bigger power units, bigger cabling, bigger anodes, all of which may not be necessary. For galvanic anodes, it's actually more serious because it has a real sustainability and environmental impact, because we calculate the amount of mass that we need to last the anode life by taking the mean current density. And that is calculated from the mean coating breakdown. So the mean coating breakdown there will be something like 5 times the amount of current that we actually need. And the anode mass is directly related to the current. I've got a young lady here who's telling me what to do and how much time I've got left, just like my sat nav. Or I sometimes ignore her too. Sorry. So we have a problem, and this is a design problem which at the moment we have no answer to, because we don't know what the rate of absorption is through a coating system. And why don't we know? Because you guys won't tell us. It's essential information. We need to know it. And it has a huge sustainability impact. So this is a challenge for the future. Now, moving on to galvanic anodes, which is something I know more about. We need to know what there's two impacts. There's the downstream effect of galvanic anodes, the upstream effects. And people are getting very sniffy about galvanic anodes. They've got to be bad. We're putting metal into the sea. They work by dissolving metals into the sea. Tons and tons, as Birgit has told us earlier. So is this a good thing or a bad thing? And what happens to the metal when it does dissolve? Well, we have had studies in the past even in the 1990s, the National Rivers Authority, with now the Environment Agency, studied the effect of zinc in estuaries and marinas on the south coast and on the Norfolk coast. And they determined that zinc, yes, does go into the water from anodes. It collects more in the sediment than in the water. And that's a feature which has also been determined by the Dutch authorities when they were looking at sources of zinc and cadmium in their drinking water. There was just after the turn of the century, doesn't that sound old? But a French project called EFFORTS, which stands for Effective Port Operations, and that studied the distribution of dissolved aluminium from aluminium anodes in Le Havre harbour. They found exactly the same thing. Very little increase in the aluminium in seawater, but a noticeable increase of the aluminium in the sediment around the anodes. There's been a more recent study from the German authorities, BSH, who are the German authority for licensing offshore wind farms. They studied the same distribution of aluminium in an offshore wind farm in German waters. And the conclusion of all these studies, and particularly the zinc ones, the amount of zinc going into the waters is minuscule compared to all the other zinc that is coming from industrial sources further upstream. Try again. Well, the constituents are largely within the known variability for the North Sea. That was the conclusion. The German study concluded that there are no direct effects of the marine environment that can be currently recognized. But despite all this, there is a new project called the Impalloy project, which is an EU-funded project going to study exactly the same things again, the distribution of dissolved metals around an offshore wind farm site. Before you guys get too complacent, this study also is going to be looking at the emission of paint flakes. If you think it's bad putting aluminium ions into the water, is it a good idea to be putting paint flakes into the water, maybe loaded with little glass particles that get into the food chain? I don't know, but they're going to study it. And this is a joint project with all the countries on the eastern seaboard of the North Sea, from Norway all the way down to France. The biggest player, of course, is the UK. But since it's an EU-funded project, one of the benefits of Brexit is that, well, we can't participate. But we hope to be fed information from the project as it proceeds. It's a 4-year project, multi-million euros, and we're missing out on it. If we look at the effect of dissolving anodes, well, you can see these are aluminium anodes on a sled on the seabed, and all the bits of white on it are in fact the product of corrosion. Aluminium ions are soluble and they do disperse in the open seawater, but there is a build-up of hydrated aluminium oxide, basically, which is insoluble. And it is quite friable and it can collect, but you don't see much of it in open seawater on the seabed. You can certainly find it in an enclosed environment, such as a harbour or marina, where there is no water flow to disperse it. So the findings that we have so far well, they're not unsurprising. We would expect to see what we have seen. But are these emissions dangerous? Are they detrimental? Are they toxic? Well, there have been some very limited studies on toxicity. They have been undertaken into the effects of aluminium and zinc into mussels and so on. And they have they've only been taken in terms of laboratory studies in tanks, so not comprehensive at all. And we have a whole list of reference papers. I have a printed paper if anybody wants to pursue this topic, and I leave them upstairs at lunchtime, or you can contact me directly. But so far, all these studies have shown that there's very little impact. There was a paper published in 2018 by a guy called Kirchgård, which is widely quoted by the NEIMME project, and they said that currently there's no clear evidence of a negative impact on the environment. In 2020, there was a paper published on the effect of dissolving aluminium and zinc from anodes on 3 separate marine organisms. Again, the impact was not indicated. Now, I know that there is much more research to be done, but it fills me with hope that there is actually no negative impact of dissolving aluminium anodes and zinc. There may be with zinc anodes, because whilst the World Health Organization says zinc is not particularly harmful, you have to ingest directly a great amount of it for it to be harmful. The big problem with zinc anodes is that it contain cadmium, and it's the cadmium which is really toxic. But the good news is that we have developed alloys which are zinc alloys which are cadmium free, and we have developed aluminium anodes which have a very low level of zinc in them. And in the new standard ISO 9351, which Birgit referred to, those alloys are included, and they have more or less the same performance parameters as the existing anodes that we use, so that we can have some confidence in the future. So if the downstream impacts of anodes are not particularly worrying to me as a manufacturer, the impact really must be upstream. Can I? No. So we have 2 upstream impacts. One is from the actual primary metals. We use aluminium and zinc. It has to be mined, and then it has to be refined. The mining is determined by location, where the ore happens to be. But because things like aluminium are produced from an electrolytic process with molten bauxite, then it's very energy intensive. So it turns out that bauxite might be mined in one location, but refined to primary metal where there is a better source of power. And that could be anywhere in the world. We have to look at the subsequent effect of the anode manufacture. And again, it's very energy intensive. Melting and casting operations do take energy. There is also the transport effect. We have a current contract where we're taking aluminium from the UAE, a smelter in the Emirates. It's going to European warehouses, Rotterdam or Liverpool, as primary metal. We buy it, we take it to the West Midlands, we make anodes from it, and we're shipping the anodes to the Gulf of Mexico. The stuff is going all the way around the world, halfway around the world. So it must have a sustainability impact. And those are the impacts that are never captured anywhere on these EPDs. So there's a huge hole and a huge discrepancy with these EPDs, if you can find one in the first place. Some of the smelters will in fact tell you what their CO2 equivalent is in terms of tons per ton of metal. But they vary widely. The Emirates, for example, is something like 8 tons per ton of metal. If you go to the French producers, it's down around 2. So that's got to be a recognition or a result of the different power sources that they both use. So what can the anode manufacturer do? Because that's the only control we have. We can't change anything else. Well, the UK government tell us what the impacts of energy impact is, and the fuel mix on an average. UK suppliers have to publish what their fuel mix is in the same format. And you can see that from the average, I've picked out 2 random suppliers in terms of overall CO2 impacts. They can be very different. And obviously the EDF one is a feature of the nuclear power source. But the UK government are telling me that nuclear and renewable power don't have any CO2 impact. Well, what a nonsense. That's an absolute nonsense. Does anybody think you can build a nuclear power station without leaving a carbon footprint? All those tons of resins going into turbine blades, does that not leave a carbon footprint? Well, of course it does. But this analysis doesn't take into account life cycle assessment. And we have to be more clever looking at the whole life cycle of the products that we're using. I'll quickly go through.
Winston, you might have to let people read it if you
Yeah.
run out of time.
All right. Well, I need to just can't get this thing to go at all. There we are. This is just what the manufacturer can do. You can see some step changes, and I'll push on because what it does mean is that by careful analysis of what we're actually doing in manufacturing terms, we can affect our carbon footprint.